In this video, we're going to continue our analysis of the Smith chart. I think it's important if I do a general analysis, and if we take a look at the Smith chart in some detail here, just so we understand what are the key points on the Smith chart, what is important to understand. So the first thing we notice about it is it's a big circle, and all these circles right here, if you take the biggest circle right here, hold on, so if you take this largest circle here, it corresponds to a load impedance of or a load resistance of 0. And then as you go into the inner circles here, the resistance increases. Notice that this is the normalized resistance. So this circle here is for the resistance equals 1, the normalized resistance equal to 1. And then the other circles, as you go to the right, the resistance increases and tends to infinity. So the second thing is all these pieces of circle that go up right here, these are the inductances, normalized inductance, and this is the normalized capacitance going down. So that's the second thing. Now, when you want to find a certain reflection coefficient, you first find the normalized load. So you go here to find the resistance, you go here to find the inductance, etc. You mark this point, then you find the distance from the center here to here. You find this distance here, let's say it's x. You divide x by the total radius of the chart. For example, this is the radius, let's say this radius is y. So this value, this length here, should be equal to x over y. And this is the absolute value of the reflection coefficient, so it's the absolute value of gamma. Then you find this angle theta here by extending the line up to here and finding what the angle from this outer circle here. Okay, so that's the second thing. Oops. So that's the second thing. Now, one of the most important and useful features of the Smith chart is this the outermost ring outside here. This ring here gives you a fraction of wavelengths that you can go along the transmission line. So let's say, for example, that we have found the reflection coefficients for a certain load, and we have found the reflection coefficients to be given by this point here. This means that the reflection coefficients exactly at the load will have this value here. So what would happen? What if you wanted to find the reflection coefficient at a certain distance x away from the load? You would have to use the formula. Remember the formula, R0 times e to the minus 2j beta x. This is equal to Rx, which is the reflection coefficient at a position x. However, if you use the Smith chart, it's much easier. What you do is you extend this line up to the outer circle here, and if you look here on the Smith chart, it says here wavelengths towards generator and then wavelengths towards the load. So in this direction, if you go in this direction, you go towards the load, and if you go in that direction, you go towards the generator. So if your reflection coefficient at the load is at this point, and you want to know the value of the reflection coefficient at a certain distance x away from the load, let's say you want to find the distance at a quarter wavelength distance away from the load. What you do is you come from this point here, you go around until you have found a certain fraction of wavelengths, number of wavelengths away from the load that you want. So let's say you came up to here, then you draw it back to there, and then you find the original length, which is this point here. So you just take a compass and you go around like this, and this will be your reflection coefficient at that distance away from the load. And of course, you can also find the input impedance by finding the intersection of these, where this point here intersects with this these lines here, this and the circle, and then you will have found the input impedance at that point. Now notice that this chart here, let me just delete all this stuff. notice that this chart here, if you go half a circle, half of the circumference around, this is equal to 0.25 wavelengths. So the full circle is equal to 0.5 lambda, and half a circle is equal to 0.25, which is a quarter, and the full circle is a half of the wavelength. So it doesn't matter how far you go, you can go full circle, and then you can go another full circle. That will be equal to a distance of lambda away from your load. And of course, you know that lambda times the frequency is equal to the propagation velocity, so you can calculate lambda from the propagation velocity divided by the frequency, and then you can calculate the actual length of your transmission line by using the formulas for the speed of light, speed of propagation, and you will find the actual length of your transmission line. So this is why the Smith chart is so helpful. Now, we want to understand where these numbers here come from. Why are they in the Smith chart? How do they know that if you go half circumference, you will have run the distance of a quarter wavelength? So this actually comes from this formula right here. It's staring us right in the face. So if you look here, this is Rx, the reflection coefficient at a distance x, and so the term at the exponents of the exponential here is minus 2j beta x. So that's an angle. So we can write that theta is equal to minus 2 beta x, which is our angle. And so here we have a relationship between an angle and the distance, which is x. So remember that beta is equal to 2 pi over lambda, and so your angle is going to be equal to, let's forget the minus here because this is just the direction of the angle. So theta is equal to 2 times 2 pi over lambda times x, and so this is equal to, choose another color here, this is equal to 4 pi times x divided by lambda, which is equal to the angle. Let me go down here. So this is 4 pi times x divided by lambda is equal to your angle. So what we have here is a relationship between the distance, the wavelength, and the angle, an angle. So this means we can map this into a circle, which is exactly what they do with the Smith chart. So, however, let's say using x sometimes not very useful, so we can write x to be equal to a constant k times the wavelength. So this means that if k is equal to 1, then x will be equal to lambda. So our distance will be 1 wavelength. So if k is equal to 2, then x will be equal to 2 lambda. So for this purpose, we can forget about x and deal just with k. So we can substitute into here. So this is 4 pi times k times lambda divided by lambda. So this lambda cancels with this one. So this is equal to 4 pi times k, which is equal to our angle. So let's suppose that our angle is equal to pi over 2, which is equal to 90 degrees. What value of k will we have? So 4 pi times k is equal to pi over 2. And so this pi cancels with this one. So k will be equal to 1/8, which is equal to 0.125. So this means that an angle of pi over 2 maps to a k of 0.125. So if we go here, an angle of 90 degrees maps exactly to 1.125, which is in between 0.12 and 0.13. So this is where this comes from. And of course, if you have k equal to 0.125, that means that your x is equal to 0.125 times lambda. And so if you know lambda, you know x. And so this is how this is useful right here. And so that's what I wanted to talk about in this tutorial. I hope you have enjoyed it. Thank you very much for watching.